Section 7.2 refers to electrolytes and non-electrolytes. Actually, the most important part of this section is at the very end when we start talking about the number of ions in a solution, because that actually has a lot of biological ramifications. But we're going to talk about what they are to begin with. An electrolyte, by definition, is something that creates an electric current. So when we're talking about strong or weak electrolyte, we're talking about how much it can conduct an electrical charge. Non-electrolytes don't conduct any electrical charges. And what it really comes down to is how much the compound breaks apart. An electrolyte conducts electricity because of the fact that you'll have positive charges and you'll have negative charges. And once those are dissolved in water, they're able to move around. Electricity is essentially the movement of electrons, the movement of a charge. Well, since these charges here can move around, then automatically that means that it can conduct electricity. You'll notice when we start talking about weak electrolytes, some of the molecules stay together and some of them split apart. Whereas with non-electrolytes, they stay as wholes, they don't split apart at all. So what this is coming down to is strong electrolytes are ionic compounds, whereas weak electrolytes are typically more of a polar compound, and non-electrolytes are nonpolar. So the information that we've learned in the last couple sections still are relevant in this one. So let's take a closer look at strong electrolytes. You'll notice NaCl here. It's a salt. If you look on the periodic table, Na is here, Cl is here, Na is the metal, Cl is the nonmetal. And if you look at the charges at the very top of the rows, Na is a +1 and Cl is a -1. That means it's an ionic compound because 1, it has charges, and for 2, you have a metal with a nonmetal, which means that the metal is giving the electron away to the nonmetal, and that's making it a +1 and a -1, as you can see on the right-hand side. When they say it disassociates in water, what they mean is that it's breaking apart. So NaCl is disassociating to be Na plus and a Cl minus. Aq means aqueous, which basically means dissolved in water. Okay, so you'll notice that it's a +1 and a -1. Those charges are now, because they're floating in water, can move around, which then conducts electricity. If you also notice, we have a +1 and -1, that means that they cancel out. But what if we had a situation where it's CaCl2, where you have 2 chlorines and 1 calcium? Well, if you look on the periodic table, calcium is in the next row with the +2 charge. So on this side, it's going to be Ca2+, and Cl is still a -1 because of what row it's in. However, because of this 2 here, that 2 comes in front. Another situation that you might be curious about is when we have polyatomic ions. So for instance, if we have PO4, which has a -3 charge, that stays as a set on the right-hand side. So if we had, I'm running out of room. If we had Ca3PO4 breaking up, we'd have 3 Cas and 2 PO4s, all of which are aqueous because they're dissolved in water. So if we take a look at how things split apart, separate the positives from the negatives and figure out what the charge is. You figure out the charge by looking at the periodic table. You know that calcium is a +2 because it's in this row. You know that chlorine's a -1 because it's in this row. So that means when we break it apart, it's going to be Ca2 plus and Cl minus 1, with an AQ saying that it's dissolved in water. Notice that 2's down here. That 2 didn't come across, it came in front when it came across. So if we're looking at that answer, we know that the answer is C. Notice that they try to trick you on B, saying that it's at the back. But we know better than that. The only time those little numbers come across is when it's a polyatomic ion. Which is in the next example. Once again, we look at the periodic table, we find that K is in the first row, which is making it a +1. So there's our positive, here's our negative. Notice that there's more than two capital letters. That means you have a polyatomic ion in there somewhere. PO4 just happens to be phosphate, which is PO4 with a -3 charge. So we have potassium and we have phosphate. Both of them are aqueous. Now finally, we have another 3 over here that did not come across, because K was not a polyatomic ion, so that means that subscript does not come across. Instead, it comes in front of that ion. So that gives us A. B is trying to say that it doesn't dissolve, but we know better than that because it's an ionic compound. And C is saying that the phosphorus and the oxygen separate. We know better than that because it's actually a polyatomic ion that stays as a unit. And there's our answers once again. Now, a weak electrolyte dissociates only slightly in water. In other words, sometimes it's going to stay together, sometimes it's going to break apart. Notice the recombination. It has an arrow going backwards, so it's going to break apart and then go back. So because it has fewer charged particles, it doesn't have as much to move around, as many chances to move around. So therefore, it's going to be in a weak electrolyte rather than a strong electrolyte. And the non-electrolytes don't dissolve at all. So it says dissolve as molecules. That means that when we get to the right-hand side, it doesn't actually form charged particles. The particles have to be charged in order to be an electrolyte. And so because they're not charged and because they're not electrolytes, that means they do not conduct electricity. So here's some examples of an electrolyte. And these are the times when it's actually starting to get important. For instance, strong electrolytes would be sodium chloride. That would be important if somebody's starting to get dehydrated and they need more sodium in their body. Or another one that's very weakly would be like water, ammonia. And the things that don't separate at all, things that don't conduct any electricity, are like sugar. It's the strong electrolytes that we're going to focus on next because those are the ones that have medical issues or medical benefits. And that's when we start talking about equivalents. Notice that each time we're talking about actual electrolytes, we're not talking about non-electrolytes. With the equivalents, it has to be an electrolyte. So electrolytes right there. The equivalent is basically saying how many charges it produces per mole. How much charge per mole. So if we're looking at sodium, it has a +1 charge, so it has 1 equivalent because it only has a 1 for a charge. However, if we're looking at iron, which has a +3, it has 3 equivalents because it has 3 separate +1s adding together. So we have a +3 per mole. Sulfate, we have a 2-, we have a -2 per mole. So it's how much of a charge it has in the system. And we actually end up using these as conversion factors. So we're going to discuss that in a little bit. So just to give you some idea of some electrolytes that are really important for biological purposes. Sodium, potassium, calcium, chlorine. Those are all very important for the bodily fluids. Ringer's solution is something that's supposed to be equivalent to the same composition or similar ionic ratio as blood or as other fluids in the body, so that way if you need to give somebody an IV, you give that person Ringer's solution. Notice the little m. You may remember from the previous chapters, m means milli. Alright, so that means that when we say 147 milliequivalents, we're really talking about 0.147 equivalents per liter. Think of it as baseball scores. You don't say somebody's batting 500.500. You're saying they're bat 500. You're just trying to make it easier to communicate. So 4 milli would be 0.004 equivalents per liter. Also notice that if you added, never mind, the cations have to equal the anions. So if we added these together, it's 155 milliequivalents. This is actually a little off. This is 154. So to give you some ideas of maybe some IVs you might be dealing with. Once again, it's a milliequivalents. 154 sodium to 154 chlorine for fluid loss. So remember that's 0.154 equivalences. That means it's 0.154 charge. 40, so that means 0.04 charge per mole. This is that Ringer solution that they were talking about. Notice that they fixed the problem right there. Instead of having 154, they have 155. But these are what they use them for. If somebody has a low potassium level, they're going to give them an IV with potassium in it. If someone has dehydration issues, they might give them a Ringer solution or sodium chloride solution. So these are areas that you might want to take note of. And here's the concentrations of blood. We have 138 of sodium, 5 potassium, 3 magnesium, 4 calcium. Remember that's 0.004 equivalents per mole of calcium. Now when we're thinking about that, remember calcium is a +2 charge, which means a +2 charge has a equivalency of 2 for every 1 mole. That's important. So that means that when we're looking at the comparison of equivalency for calcium versus something like potassium, you're going to need half as much calcium because of the fact that it's a +2 and not a +1. Once again, down here, 110. That's for chlorine. That's 0.110 equivalencies per mole of Cl minus. That means you have 0.110 negative charges for every mole. Notice that the anions are the same thing as the cations. They have the same amount. Alright, so let's take a look at some practice problems with these. if we're looking at 1 mole of iron 3+, because of the fact that it's 3, the equivalency is going to be 3. That means for every mole of iron 3+ we have an equivalency of 3 charges. Now let's get a little bit more complicated. We notice that sulfate is a -2, which means it has 2 equivalencies per mole. If we have 2.5 moles of it, how much of the charges do we have? Well, you're going to set it up just like a conversion factor. 2.5 moles over 1. We have moles on top. This becomes a conversion factor of 2 equivalencies is equal to 1 mole. That means we're going to put 1 mole on the bottom and 2 equivalencies on the top. So 2.5 times 2 is 5.0. And then finally, for our third one, we have an IV bottle. So this is something that's actually directly pertaining to your future profession of NaCl. If the Na plus is 34 milliequivalents of liter, remember the positives have to equal the negatives. They have to have the same equivalency. So that means if there's 34 sodiums, that means there has to be 34 chlorines. And that's the end of section 2.